Hello, and welcome back to Physics with Mr. Elliott, Finals Revisit. Today we're going to talk about electrostatics and magnetism through two problems. Those two problems are in your notes, in your final review packet. Make sure to follow along and answer the questions as I go through the strategies required to answer those questions. Take down some notes and be prepared for Monday to do similar problems in class. Make sure to text and email me if you have any questions. Alright. So the first problem we're going to do is a number line problem. I read the question first and I see that I have 2-point charges on a number line. The first charge is positive, 1.2 MC. This M we know means times 10 to the negative third. It's micro, negative third. It's micro. You can look on our equation sheet, cheat sheet part to see if that works that way. We also have our second charge, which is negative 2.6, again micro. So again, times 10 to the negative third coulombs. And I'm going to use that to answer these 4 questions. 5 questions. First one, calculate the electric force between the two charges. The electric force is an equation between 2-point charges. That's what I'm looking for. And I look on my equation sheet, or I remember, or I know that the force becomes K, which is a constant, Q1, Q2, K, Q1, Q2, over R squared. I'm going to use this equation to solve for my force. But the biggest thing that's important is that I know these two Q's, it doesn't matter if they're positive or negative in this equation. We find direction of force by looking at if they attract or repel, not by looking at their positive and negative signs in the equation. So we go back and we see that, whoa, alright, I see that I have a positive and negative charge. I know they're going to attract. That's what I use the positive and negative for. So I go to this. Now, how do I find R? Well, I go up to the top and I see how far apart are these two. Well, one is at negative 0.1, the other one is at 0.2. So it tells me that my R equals 0.3 meters. I'm good to go. Solve that question. I'm going to give you a second to solve that question. Part B, draw a diagram of the two electric fields from Q1 and Q2 at point P. So now we're talking about electric field. Electric field is from 1-point charge, in this case, wants to know the direction of the electric field. So I'm going to have 2 directions. I'm going to have one from Q1 and one from Q2. So draw almost like a free body diagram. I'll have one for Q1. So I look here and I see Q1 is equal to positive 1.2. So this one's positive, and we said this one is negative. So the electric field always goes away from positive and towards negative charges. So in this case, it's going to go away from this. We're going to label it as E1, the electric field from charge 1. I also have this one. We'll go away from this. Oh, no, it will not. I see that I have a negative charge. It will go towards a negative charge, and that will be E2. That's all I have to do for part B, because I'm drawing the diagram of the electric fields. So when I look at this diagram, it says when I find the total electric field of the net, all I have to do is add them together. But one is going to be negative, because electric field is a vector. And I see that the direction is going to the left for E1. So my net electric field would be E2 minus E1, which will bring us to part C. Calculate the net electric field. So our E field is going to be E2 minus E1, because this is going to the left. I use my electric field from E2 and from E1. Well, I don't know what E2 or E1 are yet. I need to use my equation. I go back, and remember, from a point charge, the electric field equation, E equals K, same K from before, Q over R squared. It's the force equation without the second Q. So that Q, I can do it twice. I'll do it for Q1 Q2. And that R, that radius, is the distance from point P to the charge. From point P to the charge for Q2. So these two R's should be different as well. So you're going to go ahead and find E1, find E2, and then use this to find the total electric field. And your answer should be given in newtons per coulomb. That's your units. If you're forgetting what K is, K equals 9 times 10 to the 9. So, moving on to part D. Calculate the total electric potential at point P. Different. When I read electric potential now, I know I'm solving for V. That's another word for voltage. We use it differently in different cases. But the electric potential from a point charge is the voltage from that point charge. It's K, Q1, or whatever Q, over R. Now the difference between this electric potential equation and the other equation for electric field and electric force is that you put in the negative or positive for the charge because it's not a vector. There's no arrows. We only put in for the charge. So, we're going to do this for V1. We'll do the same thing for V2. We'll do the same thing for V2. And then we have to add them together. V2 is going to be negative because I have a negative charge. So I'll put a negative charge in here. That'll give me a negative voltage. I add that negative voltage with the positive voltage for V1, and I'll get my total. So V net equals V1 plus V2. We'll go to a different color. So voltage from a point charge, KQ over R, is not a vector. That's why we don't have absolute values here. We have to put our negative and our positive in for the charge. Last one, calculate the net work required to bring a 1 nanocoulomb times 10 to the negative 9 point charge from infinity to point P. Now this from infinity part, all that tells us is that the initial energy is equal to 0. So that just helps us find the equation we need to use. Work is equal to change in energy. So that means that if we start with 0, work is going to be whatever our energy is. Well, instead of energy, we have the potential. The potential is related to the energy just by the charge that you're moving. So work equals Q, the charge moving, times V, your change in V. So your change in V, you started out with no energy, started out with no voltage. Your change in V will be whatever you got in part D, because that's at point P. And you get your work. And that's your answer. Remember, work is going to be measured in joules. Just like energy. How much energy is that going to take to bring it from infinity to point P? The infinity part, again, just tells us that we start with an energy of 0. Alright, so now that you've finished problem number 8, you want to make sure that you're set. You go ahead and get your answers, check your work, and then you can make sure to email or text Mr. Elliott if you need any more questions, if you have any more questions. Me, that is. Let's look briefly at number 10. Number 10 is a similar problem, but now we have a magnetic field involved. So we're going to talk about this one. An electron is fired from a hot filament, cathode ray, tube, and is accelerated through a potential difference of 100 volts. This is another term for voltage, right? It then passes into a region of uniform magnetic field, 8 teslas, directed into the page as shown above. The mass is this, and the charge is that. Awesome. So I want to know, first, find the speed of the electron after it's accelerated. So we know that the voltage here, the voltage is 100 volts. We know the electron, it's accelerated. It's accelerated by the electric potential energy. So the work done, again, is exactly what we just had in the last chapter. It's Q times the change in V. And that work is going to give the electron energy. And that energy goes into, instead of just being work, it's creating kinetic energy because it starts to move it. And that's how we're going to find the speed of the electron. Ke is now going to be your Q delta V. Whatever I get for work, I'll plug in and set equal to Ke. And then I use my equation 1/2, 1/2 m v squared equals Q delta V. I'm going to solve for this velocity. Remember, these two V's are different. This is voltage, this is velocity. Don't confuse them. I'm going to solve for this V, the velocity, using everything I'm given. That will give you your answer. Because we know we accelerated by a potential difference, that gave me energy from the potential difference, which is work. That energy is just Ke, and I get it that way. Part B says, on the diagram, sketch the path of the electron in the magnetic field. So now I have to think about, once it enters the magnetic field, how's it going to move? And we know we have a specific rule for it. It's called the right-hand rule. I hold it up here. I have my force is indicated by my thumb, and that's what I'm going to look for because it wants to know the path. So I need to see the direction of the force. I have my index finger, which is the velocity, going to the right in this case, and the magnetic field, which are my 3 fingers here. So you hold it at 3 90-degree angles. Your magnetic field goes into the page. Your thumb points up, your finger goes to the right, so that means that your force is going upwards. But that's for a positive charge. For a negative charge, we flip it. So I know now, once this enters, it's going to have a force that's going downwards, a magnetic force. So it enters the magnetic field. I'm going to draw this in blue. Comes in here, enters. It gets a force, pulled it down. But as it goes down, it moves in a circle. Because if it starts to go down, you see that if it starts to go down, you see that my finger still, as it turns, to keep this 90-degree angle, you're going to have to keep turning in a circle. Your force will point towards the center because they're always perpendicular. So that means that this enters and moves in a circle like this, eventually hitting the end there. So you have to, in order to get full credit here, you just have to draw it in a circle and make sure that you make that clear. Find the radius of the circular path. So now we know it's a circle because it's C. We have to find the radius. Well, to find the radius, we use our circular motion equations. Sigma F equals mv squared over r. That's where we're going to get our radius. Sometimes it's hard to think about that. You think, all right, radius what? Use your sigma F equals mv squared over r of the electron. Now, if I use that, I can solve. Where'd you go? I can solve for r, but I don't know what F is. I do. The only force on it is that FV. And we know FV is equal to Q V. This V is velocity. It's not voltage. That will be your velocity. Whatever you find in part A will be plugged in right here in part C. So, same with this velocity. It's the same thing. So I have QVV equals mv squared over r. And the way that you go ahead and finish this is you're going to solve for r. Manipulate. Remember, get it out of the basement first. Do not try and get rid of mv squared. Get r out of the basement first and then solve for it. You'll notice that v's cancel out a little bit. You solve for it that way. Last but not least, we get into part D. Part D tells us now we create an electric field. So for instance, if we want to make it go straight, it said, right? So that the electron passes through the region undeflected or continues straight. We have to create an electric field, we'll say using 2 plates. We want to know what is the magnitude of that electric field and what is the direction to make that electron go straight. Well, the direction of the electric field, we know the electron is getting pulled downward by an FV into upwards FE. So we need a force going upwards. We also need force going upwards that's going to create the electron to move straight. So what that tells us is that our electric field should be pointed upwards if that was a proton. Because our electric field between these plates will always be the direction a proton would go. It's going to go opposite. So we know that our electric field, E field, would have to go down. So the E field would go downward. making a force on the electron upward. That's actually the second part of this question. The first part, find E. To find E, I can't use any specific equations that I have, right? KQ over R is only for a point charge, the change in voltage over time. We don't know that. But what we do know is that in order to make this move, FE and FB are equal. They have to balance out. So FE equals FB. Now FE will be equal to the charge of the electron times the electric field. FB is Q dB. Now you can solve for E. And quick hint, cancel your two Q's because they're the same. You get E equals V times B. Well, you know what V is from part A, you know what B is going to be. So that's how you go ahead and finish that problem. Get an answer. Crush it out. Make sure that you're focused and you have the right V and you're using V correctly. So our key takeaways from these problems are that we have to start to remember about the motion of electrons in magnetic fields, circular motion, and electrostatics. If you have any more questions about either of these problems or any of these topics, make sure to email them, send them a text, or go ahead and get at them on Twitter. All right? Have a wonderful weekend, and I will see all of you Monday, really ready to get some more practice in so we can crush our final exam next week.